last time we summarized chapter 5, and I prepared several problems for you to play with. Okay, the first one already, saw the answer. Okay, so this is just an exercise, right? They have true or false, then multiple choices, single selection, multiple choices, multiple selections. Okay, so number 1, true or false, right? The power efficiency for double sideband large carrier always less than 1. Yeah, true, right? We mentioned efficiency. M squared, right? This is efficiency for double sideband large carrier. You can find the equation in your table, in the summarized big table. So always less than 1, no matter how big is M you choose, right? Definitely M will be a number less than. So it's true. Okay, look at this one. AM, double sideband modulation, has 2 times of bandwidth compared with the original signal's bandwidth. So we call it double, right? Double sideband, because the bandwidth is twice of the original signal's bandwidth. For double sideband suppressed carrier modulation, we can use envelope detector as receiver. No. Only large carrier we can use envelope detector, and for this one we have to use coherent detector or synchronized demodulator. Okay, here multiple choices, single selection, just one right answer for those couple of questions. AM, amplitude modulation. Which component of your signal of your carrier is controlled by your message modulating signal XT? Phase, frequency, or amplitude? Amplitude, right? Because this is AM. So if we change frequency, this is what we're going to talk about in chapter 6. Frequency modulation, right? If we play with phase modulation, also we will talk about in chapter 6. So the rank is C. Okay, here, coherent detection or synchronized demodulator of single sideband AM signal. Which filter is used in your demodulator? High pass, down block, low pass. Okay, if you go back to a table, table. We have mixer, then low pass, right? Yeah. Low pass filter. Okay, so low pass filter, still C. Okay, this one, multiple choices, multiple selection. You have more than one right answer to fit this this problem. Okay, equation is here, right? The power efficiency or energy efficiency of AM double sideband large carrier depends on something, right? Something. Carrier amplitude, carrier frequency, message, right? M, index, or message bandwidth. So you have more than one right answer in this problem. Yeah, so how about message bandwidth? Yeah. Oh yeah, right. First step. Bandwidth. How about bandwidth? We have M, right? We have M. So modulation index does matter, right? Very important parameters. How about carrier amplitude? A is not there, right? So it doesn't matter, right? A will be cancelled. How about carrier frequency omega C? No. How about message format? What is my signal? Triangle wave, square wave, sinusoid, or speech, right? Really does matter. So M and FT. what is your real form for your message. So C and D will be the. So I'm thinking, put multiple choices, single selection in your quiz. So yeah, so we can try. We can try that. Okay. Any concerns or suggestions?
From the
Yeah.
chart that you made last week,
Yeah.
I think you said for double-sided and suppressed carrier that the demodulation is the low pass filter.
Yes.
Oh, but I upgraded you to say it was a coherent.
Coherent detector. What did I say?
I think you said it was the coherent detector.
Okay.
Suppressed carrier, and then you said that SSB was low pass filter, like caution filter.
Same thing, right? So right now I don't have the table with me. So for double sideband large carrier, we can use envelope detector, right? For all others, let's see, double sideband suppressed carrier, single sideband OVSB, we all use coherent detector. Okay, also called synchronized detector, the same thing. Low pass filter is an element in this detector. So we can find low pass filter in the receiver because low pass filter is a part of your coherent detector. So in this problem, right, we just ask one element in this receiver. So we still need mixer, right? We still need reference, retraction, or phase lock loop. Okay, any other problem questions? So now we talk about FM and PM. So when you drive, right, you listen to your radio. If you have FM station available and AM radio station available, generally you choose that FM. Why?
Sounds better.
Yeah, exactly. So we are going to learn why it's better, right? Why it's better, and achieve this better performance. What we should pay, right? No pain, no gain trades, right? So we're paying something for the better performance, and we really get those better performance. Okay. So last chapter we talked about we change amplitude, right? Just we mentioned amplitude is controlled by your message for AM. For FM and PM, we change frequency or phase. Okay, this is the equation we used before, right? If we play with AC, keep omega C, zeta T constant, it will be AM. If we keep AC for constant, play with the entire thing in this breeze, we call it angular modulation, and we have two members here, PM and FM and PM and PM. So here, many details. We are going to go back, talk about those details. So just a quick introduction. We view XT as our message. So for PM, my phase is linear proportion to message. We call it PM. For okay, let's skip this one. Let's skip this one. Okay, later we go back to the first slide. Okay, before we talk about what is FM, what is PM, we want to know phase and frequency, they are related. phase is integral of frequency. Frequency is derivative of phase. And also we know, right? Frequency, reading per second, frequency in hertz, there is a 2 pi, right? 2 pi ratio. Okay, so for angular modulation, carrier amplitude will be constant, and my instantaneous phase is omega ct plus theta t. This is the entire thing in your breath. And instantaneous frequency is derivative. Let me write down. Okay, so incident phase actually will be okay, we call the entire thing my phase angle, right? We call this one my carrier frequency, and this one will be my initial phase, right? Initial phase where you start your signal, However, the entire thing, we call it a phase angle. If you look at your phasor, right? Your phasor amplitude is A. Phasor angle is the entire thing, including omega ct plus theta t. So we call this part my instantaneous phase. Derivative of it, we get instantaneous frequency, right? So D CT, we get omega c plus half. In my slide, we use omega t, right? Omega t. So instantaneous frequency is omega c, right? T is got because of the derivative. And omega of t, we assume this is derivative of theta t, or theta t. Okay, so phase derivation is theta t, and frequency derivation is omega of t. Omega of t. Any problems, questions from this one? Okay, here we want to show examples. The first one is information, right? Information. We have a unit step function, and this one is PM or FM. This one is unmodulated carrier. This one is phase modulation. We can find frequency kind of the same, right? But phase change when you have signal change. And here, low amplitude of your information, they have a lower frequency. Here, we have a higher frequency. So very easy for us to distinguish FM and PM. Sometimes it's not so straightforward. Okay, so any problem for this example, we have a message PM and FM. FM. Okay, this example we showed it before, and we have digital sequence as my information because this one ASK, right? Amplitude shift keying, PSK and FSK. We also mentioned, right? Control amplitude and phase is easier compared with control frequency. So different frequency you have different, right, oscillator. So you generally use ASK, PSK, or combine those two together. We'll call QAM. Where A and P change together. So this is another example, and very easy for us to distinguish A, P, and F and F. Okay. Next example may not be very. Okay, this one. So we still have signal carrier, two modulated signal. Okay, and from the picture, right, from the label we find phase modulation and F frequency modulation. How can we distinguish those two? Okay, I'm going to tell you a trick. So, let me write over here. For FM, my instantaneous frequency. We can the I. Omega C, this has omega C plus omega T, right? This one is so my instantaneous frequency is proportional to my message, right? Message. So higher frequency, higher amplitude of your input, I have higher frequency, right? Lower amplitude of a message, I have lower frequency. For PM, we use instantaneous phase. So we call it, theta I, right? Is so for instantaneous phase, my phase is proportional to message. However, if I look at a signal, right, it's really hard to tell what is my phase. So here, so we can see, okay, let me write down, this is my frequency. So my frequency is proportional to how fast your signal change. So if your signal change faster, my frequency for this signal, for my carrier should be bigger, right? If my change is slower, frequency associated with this time will be lower. So for PM, right, when it change, let me see. of the phase modulation. So we actually look at the trend of your signal. So when it change faster, we have the high frequency. When it change slower, we have the lower frequency. So generally FM is a little easier to tell. The other one generally you can see that is FM. So PM, your frequency is proportional to your message. And then PM, your frequency is proportional to the change or the trend of your message. Okay, not required, but you will just tell you something. Okay, so another example, right? AM very easy to tell, right? And amplitude is changing. For PM and FM, you can just look at, right? Higher frequency associated with high amplitude, that will be PM, and that will be FM. Change faster, I have higher amplitude, will be PM. So we show several examples of PM and FM signal. Okay, any questions?
So with PM, we have changing frequency and changing phase?
Yes.
Okay.
Yes.
When are we changing phase?
Actually, for angular modulation, phase and frequency, they are continuously changing. However, if frequency is proportional to your message, we call it FM. Phase is linear proportional to your proportional to your message, we call it PM.
Okay.
So if you change your frequency, right, your phase is definitely is also changing, right? So we cannot fix. You can fix initial phase, but you cannot freeze the entire phase of the signal.
Okay.
So your phase is continuously changing.
So notice there, like, the frequency is changing and then sometimes the phase is changing, like...
Yeah, here because we have a very abrupt changing in your message. Yeah.
Okay.
Yeah, for your message. But for FM, there's continuous, right? There's continuous in your carrier phase. Carrier phase is continuous. For PM, right? This one is very close to double side bisection carrier, right? Phase reversal, right? Phase reversal. So when your signal dramatically past zero, PM there will be a phase 180 degree phase change. So similar to this one. So for this one, right, we have a dramatic phase change because your signal dropped from 1 to 0 or from 0 to 1.
Okay.
But if you find there's dramatically changed in your phase, that pretty much will be phase modulation. Frequency of your phase is continuously changed, but the entire signal's frequency and phase actually changed. Okay. We talk about more details later. Okay, over here. FM and PM. Oh, one more thing I want to mention. So this chapter, we focus on FM because analog communication, we always care about, right? FM. So PM is not so popular in analog, but much more popular in digital communication. So when we talk about FM, most of the time we talk about FM. So the angle of sinusoidal signal is described in frequency and phase angle. So for FM, so this is talking about phase and frequency connection. This is the entire phase. Phase for your phasor, right? This is phase for your phasor. this is initial value, right? Theta 0. And frequency integral, we get phase. We get phase. Omega tau, we call it instantaneous frequency. Yeah, similar to the one I wrote over there. Okay, and instantaneous frequency is derivative of your phase. So d theta dt, we get instantaneous frequency. Okay, so if this is a phasor, right, this is a phasor, we have amplitude, phase angle, and how fast is rotate will be my frequency. Okay, this one is important. We are going to have an example using this equation. Problems, questions? Okay, let's take a look at this example. This example is from our textbook 6.1.1. We have a given signal. We try to find the instantaneous frequency of a given signal. Phi t, a cosine 10 pi t plus pi t squared. So a is a constant, right? Definitely we can tell this is not AM. It will be either PM or FM, depending on your input signal. Yeah, so we try to find instantaneous frequency by using derivative of U phase. So here, the phase mentioned is the entire phase angle. Not only the initial phase. Okay, phase angle, we just copy the entire thing in this brace, is 10 pi t plus pi t squared. So we get theta. Then instantaneous frequency will be derivative of d theta dt, right? So we have 10 pi plus 2 pi t. This is my instantaneous frequency. Instantaneous frequency. We can find it's linear, right? To time. Okay, so it also mentioned that when t equals 0, when t is 0, my frequency is 10 pi, so that means 5 Hz. The frequency is 5 Hz at t and increase linearly at the rate of 1 Hz per second, so 2 pi per radian second. Thus, critic phase shift gives a linear frequency dependence. So we have linear, right? Linear frequency, linear frequency, project phase. So phase is the integral of this one, the dimension. This is the change of how fast you change in your phase, Later, if we have similar problems, follow 2 steps. Step 1, just find your frequency, find your phase, then calculate the incident frequency by derivative of your phase. So step 1 and 2. Okay, now your turn. So I want to find the instantaneous frequency for this given signal. So phi is 5 cosine 20 plus sine 5t. So remember the step 1, step 2, 2 steps. You have 3 minutes. Okay, so for this one, let's just, go through it together. Okay, so step 1, right? Step 1, I find my phase. So here is my phase. 10t plus sine phi, we just copy the entire thing over here. So instantaneous frequency will be d theta dt. Okay, 10t we get 10, right? 5 cosine 5t. So this is my instantaneous frequency. When we ask when t is 0, omega I 0 will be 10 plus 5, right? Cosine 0 is 1. So 15 radian per second is my instantaneous frequency. Step 1 always between you phase. Step 2 calculate instantaneous frequency by calculating the derivative of your phase. So here we kind of talk about phase and frequency. They are related. When you change one, another one will be changed definitely. So how can we tell it's FM or PM based on the relationship between phase or frequency with your message? So here in those 2 following slides, we talk about PM and FM definition. So the first will be PM, phase modulation. So my phase is linear proportion to message. Okay, omega CT is still there, theta 0 is still there. However, there is a linear relationship embedded in your phase. We call it PM. And instantaneous frequency for this kind of signal, right? d theta dt. Omega CT derivative will get omega c only, and here we have df dt. Kp is a constant. So like you have a baseline, right? The frequency will be kind of oscillate around it. How far it will be differentiated from this omega c by 2 things. One is how big is your information record, is this one, and the constant you choose. Later we will give it a name called peak phase deviation. We'll talk about that later. So this is PM. Just remember, your phase is related with the message in this case. Okay, any problems? Any questions? Okay, now FM. FM will be the most important thing in this chapter 6. So for phase modulation, FM, my instantaneous frequency is linear proportion to message FT. Omega c, right, still like a baseline, and your frequency will be differentiate from the baseline depending on KF, this constant, and FT, your message. Generally, right, higher frequency mean you have higher amplitude in your message. So instantaneous phase will be integral of my frequency. So here we have omega CT, right, theta 0, and here is the integral of my message. So if you look at your signal's phase, will be the continuously change, accumulate, right, by your message. So this is frequency modulation definition.
The integral there, is that with respect to t?
Yeah, should be d. It should be tau, d tau.
Okay.
D tau, yeah. T, right, will be starting from 0 and towards the current time. Yeah, I believe d tau is missing. Let me see if I can add d tau here. Okay, so yeah, so please add to the printout slides, and if you have your note, then just add detail to your note. Okay, here is an example that we have. This is picture from our textbook. So for two different signals, we have PM, FM, PM, FM. So PM actually is easier. FM is easier to distinguish because higher amplitude always associated with higher frequency. The other one pretty much will be PM. If you really want to tell PM, right, your frequency is associated with the changing of your message. Okay, now we are going to talk about a very important thing in FM family. So there are some mathematical equations. Just try to follow me, and I'm not going to ask you to remember those equations. Okay, so this one is quite interesting and very important. This one will be the foundation for later other FM in this family. So we talk about narrowband FM, why and how. So we use sinusoid as example, trying to make our analyze simpler. So this is my sinusoid signal as my message. Okay. So for FM signal, we just write down, right? Previously. This part. 2 slides before we have, so for FM signal, my incidence frequency is proportional to message. Now I substitute my message into it. I get omega I is omega C plus A KF cosine omega MF. This one is my message, right? A cosine omega MF is my message. So we just follow it. Now we give AKF a new name. We define as delta omega, we call peak frequency deviation. Delta omega, we call peak frequency deviation. Okay, why we call it like this? So we know incidence frequency is oscillation around a baseline omega C. How far it can away from omega C depending on K, A and K. So delta omega is how far you can away from it. This is maximum value you can away from the baseline. So delta omega we call it peak. So this is the biggest peak frequency deviation. Okay, later we talk about that in more details. We're also going to use it in later some calculation. Any problems, questions so far? Now we try to okay. It's overhead. Omega. Its frequency is omega C plus delta omega cosine omega m of t. So theta t, right? So how about my phase? Okay, so phase is integral of my omega I. So we get omega ct plus delta omega over omega m sine omega m of t. Okay, so let's see plus delta omega cosine omega m of t. Oh. So we get half, we get this one. We get this one. Integral of your frequency, we get phase. And we give delta omega over omega m a new name, we call it beta. This one is modulation index. Okay, we call it modulation index. This one is very important thing, similar as m in your AM. So now theta t is omega ct plus beta sine omega m of t. Okay, now we substitute this one back to my original signal. So my FM modulated signal is A cosine theta t. Okay, now the following procedure is not required. Just try to follow me. Okay. So theta t, right, goes here. This is my signal, my modulated signal. You have cosine 1, we can have cosine A plus B, right? So we have, let me write down, we have A cosine Okay, cosine one angle plus another angle, we have cosine minus sine, right? Okay, now, okay, cosine beta, sine omega m of t is the phase of your cosine. So very complicated. For something like this, we use Bessel function to express it. However, today we try to make it simpler. So if if beta is a very small number, how small? If beta less than 0.2, we can simplify this one and this one, and let's do it together. So for a very small number here, so cosine, a very small number, approximately equal 1, cosine 0 is 1, right? Cosine, very small number, close to 1, very close to 1. This is my first term, right? The second term. sine a very small number. So have sine x. If x is very small, sine x close to the phase angle you have. So this one close to beta sine m of t. So depending because of cosine and sine. So this one becomes something like this. Now we rewrite my signal. Okay. So after we use this 2 beta less than 0.2, this one approximately equal 1. This one very close to beta sine omega m. We rewrite original signal. We have narrowband FM equal to A cosine omega because this one will be 1, right? Minus beta sine omega m of t sine omega c of t.
So that beta sine omega m of t doesn't get multiplied by a.
Oh, yeah, A is here. Sorry, yeah, A should be here. A should be here. A should be for the entire thing. Okay, so the procedure is not required, just I want to remember this one. So if you look at this one is very close to something we talked about before, right? Actually, in the, yeah. So in the slide, we have it. Okay, any problem, questions? Let's go to the slides. So we just make my equation simpler, then beta is smaller. So then beta is small. Narrowband FM, we have A cosine omega mct minus BA, beta is sine omega m sine omega ct. This one is narrowband FM. This one is double sideband, large carrier, right? So A cosine, this is my pure carrier. This is my message mixed with carrier. So pretty close. And for the structure of generating narrowband FM, very close to double sideband, large carrier. So small beta give us pretty simple equation. This one, I hope you can remember. Okay, so this is narrowband FM equation. Here is the spectrum. Original message of sinusoid, right? We have 2 peaks, 2 impulse. This is double sideband, large carrier. Narrowband FM. over half. And this figure you can also find from a textbook. So for narrowband FM, cosine, right? Cosine. This one is for sine. For sine. So spectral, line spectral, close to AM, large carrier. So this is the phasor. This is my AM, right? Double sideband large carrier. We mentioned it before in chapter 5. This is cosine, and this is sine, like the one at AM rotate overhead. So this is my narrowband FM phasor. Okay, any problem? I have one last thing want to mention today. So we call it narrowband FM, right? Why we call it narrowband? The reason is here. The bandwidth for narrowband FM is 2 times of your signal's high frequency. So W is 2 omega m, B is 2 FM. This one compared with later wideband FM is kind of narrow, close to AM bandwidth. And beta is 3 omega over omega m. We call it modulation index. I'm going to show you one example and finish this lecture. Introduce the other side. Okay, we use this one as example. So we have a message. The message is 100K per sinusoidal signal. So FM is 100K hertz. A carrier is 5 hertz. FC is 5 hertz. Peak frequency deviation is 1K. F is 1K hertz. What? Okay, we know 3 things of this FM signal. FM is 100K, right? My message frequency is 100. Carrier is 5 peak hertz, and peak frequency deviation is 1K hertz. We will find what is the bandwidth. Okay, later, for all those kind of questions, we always follow 2-step thing. Step 1. Always check your beta. Is narrowband or wideband, right? We only talk about narrowband. Later talk about wideband. So always check is narrowband or wideband. So we have 1K over 100K